So this is just a quick review of Lewis-dot structures. Lewis-dot structures are based upon the bonding of elements. And actually, if we take a look at the valence electrons of our different elements, and mainly we're dealing with the nonmetals over here. And you can see, you guys should know by now how many valence electrons they have that are used for bonding. So let's make this smaller again, since you guys know what those are. Let's just do a simple one. And I know it's very simple, but we're just going to practice with it. Let's do CH4, okay? And numerically, the way you determine that is that carbon has 4 valence electrons, and each hydrogen has 1. So 1 times, and there's 4 of them, is equal to 4. So we add the two together, and we get 4 plus 4 gives us 8 total electrons that need to be involved in this bonding. So we put carbon in the middle because it can form the most bonds with, it's going to form 4 bonds to get to 8. So, and we do a skeleton structure with our 4 valence electrons are on the outside. And each line represents 2. And so there's 4 of those. So we subtract 8 because there's 4 times 2 is 8. And we have 0 left over. And so that is the structure of CH4. Pretty simple, pretty straightforward. And so let me see if I can, oops. I'm going to make this smaller and kind of get this out of the way. Okay, so now let's do something a little bit harder. It's not that much harder, but you never know, right? Let's do PCl3. So phosphorus has 5 electrons, and each chlorine has 3, or 7. 3 times 7 is 21. So we add the 5 plus the 21, and we get 26. So we put phosphorus in the middle because it can form the most bonds. It needs 3 more electrons to get to 8, so form the most. And we do a skeleton structure around the outside of our chlorines. Okay, so for each of those, we had 2. So minus 6, 3 times 2 is 6, we get 20. Put it over here. Now, when you were looking at the outside electrons, these ones right here, right? They're chlorine, they need to have 8. All of the outside valence electron or atoms need to have 8. So chlorine's already formed its 1 bond because it had 7 valence electrons, need 1 more to get to 8, so it formed that. So actually, we would just add 6 electrons around each of these chlorines to get to 8. 2, 4, 6. Wait, hold on, let me just show it to you. 2, 4, 6, 8. Do that for all 3 of those. So that 6 times 3 is 18. So minus 18 gives us 2 left over. And phosphorus, as the central atom, it still needs 8. So we add 2 dots there. And we added 2. So we get that down to 0. So that is our Lewis-dot structure for PCl3. So let's make something even more difficult. Oops. So let me make this smaller, duck it out of the way over here. So let's do something else with PCl3. Now we're going to get to an expanded octet. Now in order to do an expanded octet, you have to have an element that is from the 3rd row and beyond, okay? Because you have to use the d orbital right here, right? The d orbital has to be accessible to make more than 8 electrons around the central atom. So nothing from the 2nd row right here can be used as your central atom to make an expanded octet. Fluorine, oxygen, nitrogen, carbon cannot be used in an expanded octet. Once you get into phosphorus, silicon, sulfur, chlorine, bromine, iodine, get a lot with iodine, also xenon, you can use some of that. Those can be used, okay? So I just want to remind you of that sort of rule. So let's put that away for right now. And let's take a look. Let's make PCl5. PCl5, okay? Phosphorus is 5 electrons. There are 5 of the chlorines. 5 times 7 is 35. Oops, equals 35. That gives us a total of 40 electrons. Phosphorus can form the most. We will put phosphorus in the center, and then we're going to add chlorines all around the outside. This is our skeleton structure. Okay? So that means we just added 5 of those with 2 electrons for each of those. That means we're subtracting 10, so that leaves us with 30. As we mentioned before, chlorine has to have 8, and it can form no more than 1 bond. When it's on the outside, you're not going to get expanded octets from atoms on the outside. So we add our 6 electrons on the outside of each of these. And so that's 5 times 6 is 30. So minus 30 is 0. So that's it. Now phosphorus has 1, 2, 3, 4, 5 bonds. 5 times 2 is 10. This is an example of an expanded octet. But given this, this is how you would set up that Lewis dot structure. And mathematically that works out. Okay? All right, let's do an ion, or no, I'm sorry, let's do one that has something on the, we'll do, a structure that has more than one something on the inside, or more than one Lewis dot structure, or more than one lone pair on the central atom. So I would like to do, let's do something crazy. IF4 minus. Now this is an ion, okay? But don't be afraid, you can still figure this out. So iodine has 7 valence electrons. Fluorine also has 7 each, and there's 4 of those, so 7 times 4 equals 28. And there is a negative here, okay, which means that we add 1 more electron. If it was a positive, we'd subtract 1, but it's a negative, so we add 1. So we add 1 more there, and so we get a total of 15, 16. We add 1 over here, that makes, so we have 36 to make. Now, iodine, as it's the element that there's only one of them. So you figure the fluorine has to be around the outside, and fluorine is one that can't form an expanded octet, so it can't be in the center anyhow. So we put I in the center, and we're going to put the F's around the outside. Okay, so, and then, I'm sorry, so I should, so 4 times 2 is 8, so we subtract 8 from that, and that should give us 28. Now we add our electrons to the fluorines. Okay, and that's 4 times 6, that's 24. So it leaves us with 4 electrons. Those extra 4 are in lone pairs on the central atom. So minus 4 equals 0. So that is the structure. So this can kind of be trippy, but that is what it would look like. And the outside atoms all have 8. The inside, the central atom has 12, right? 2, 4, 6, 8, 10, 12. But it can do this in expanded octet, and it fits mathematically, okay? So let me just give you one as a little test. You should stop the video when I do these two. Let's do IF3. IF3, and might as well throw another one out there. Here's a kind of a funky one. NO3 minus. So there's an ion and a regular structure. So go ahead and stop it right here. And then when you get back on, I will show you the correct answer. Okay, so IF3. I've laid it out here, and you can see that the iodine has 7, and there are 3 fluorines at 7 each, give you 21. 28 total minus the 6 for the skeleton structure gives you 22. 22 minus 18 for the 6 electrons that are around each fluorine. And then you have 4 left over, which you put on the central atom here. And it gives you this T structure. We'll talk about VSEPR, or the valence shell electron pair repulsion theory, here in a second. And it gives you 0. So there's IF3. So hopefully you did that. And let's move on to the... Here you can see the NO3 minus. And something that may have tripped you up a little bit was with the NO3 minus. If you'd set it up to where the skeleton structure, each oxygen had 6 on it, you would have ended with only 6 electrons in the central nitrogen, and that's not possible. So you have to do it so that there are, you put a second bond on nitrogen so that oxygen, one of them, has a double bond. And then you can work it out to where there's only 4 extra two lone pairs, 4 extra electrons on that one oxygen. Now, something, of course, I should have done is that you need to put them in brackets when you do a ion. I forgot about that. The last thing I want to show you real quick is something that if it's electron deficient. All right, so if it's electron deficient, let's say we did BH3. Boron only has 3 electrons, and hydrogen has only 1 each, which gives us a total of 6. And that equals 9, which doesn't seem quite right. So if we set this up, we get boron here, and it has 1, 2, 3. We get hydrogen on each of those. Oops, I did the math wrong on that originally. You know what? I was looking at that going, why is that possible? When all is said and done, that's 3. We're going to have 6. And so when we set this up, there are your 6. So, and that's it. Boron is electron. It's one of like just a few of them. Boron, beryllium, aluminum. Those are the ones you can get electron deficient. You don't see it very often, but it could be there. All right, so if you guys have any other questions, please let me know. Thanks.